Before we implement this paths class, let's think carefully about how we'd use it to make sure we know what we're trying to get. So, for example, let's suppose you want to know, is the vertex 3 and the vertex is the vertex 0 and the vertex 3, are those vertices connected? And if they're connected, what's a path between them? So the way we'd actually use this thing, the goal we're trying to achieve, is we'd say, hey, I want to create a paths object. I'm going to give it this entire graph, which we already saw in the 2 videos ago how you construct one of those. And we'll say, let's start from vertex 0. This is my start vertex. We can then ask our oracle here, hey, is there a path to 3? Did you see one when you looked at the graph? You inspected the graph, you held it in your hands, you sniffed it, you felt it. Yeah, oracle knows there is a path. Well, hey, oracle, what is the path to 3? Okay, well, in that case, we get back, in this case, an iterable of integers, which is going to be 0, 1, 4, 3, which is a valid path. Now, we don't know, right, in general, it would be valid if we returned 0, 1, 2, 5, 4, 3 as well. So both of those might be fine. And so it just kind of depends on how the algorithm goes. Okay, how do we actually do this? Well, the way this oracle is going to work is it's going to behave just like the example we did earlier. So we're going to do the following. We're going to go through, when paths gets created, the oracle is handed the graph, and you know, graph, okay. So it's my job to process it. I'm playing the part of the oracle. So what I'm going to do, I'm going to mark each vertex, and then I'm going to recursively visit all unmarked vertices adjacent, and there, in that way, I will gain total and true understanding of the entire graph. So example, data structures here. I'm going to have an array of booleans called marked, and I'm going to have an array of integers called edge2. And both of these arrays are going to be of length v, and the interpretation is that marked, say marked 3 is true, then we've marked it. And if edge2 of 4 is equal to 1, that means we got to the vertex 4 via the vertex 1. Okay, so let's see how we would do this in action. So this is now a deeper implementation. Okay. So this is what DepthFirstPaths looks like. This is the constructor running. So I hand the oracle this graph, and she starts thinking, okay, what's the deal with this graph? Okay, so I have 2 arrays, as I mentioned, marked and edge2. This is all false, and edge2, it's technically all zeros at first, but I'm showing it as a dash to indicate it has not yet been set. Okay, so we'll start by calling depth first search of 0, DFS 0, let's say. Okay, so in that case, what we do is we mark 0, then we say, is 1 marked? No. Okay, and oh, also by the way, then what we need to do, since 1 is not marked, is we're going to say the way to get to 1 is to come through 0. I'm at 0, I see 1, no one's been there, so I'll make a note that the way to get to 1 is to start from 0, and then I'm going to continue my search at 1. Okay, so now we get to, and I guess I have a little running tally here showing the order in which we call DFS. Okay, so next up, we call DFS on 1. And in that case, we mark 1, we've set it to true, and then we look at all the 8 neighbors and we say, okay, well, is 2 marked? Okay, well, no. So then what we're going to do is we know that nobody's ever explored 2. This is brand new territory, never considered by me, the explorer. So I'll say the way to get to 2 is to go through 1, and then we'll call DFS on 2. Now you might say, what about 4? Well, this is a depth first search, so we're considering all of the items in this direction before we go this way. Okay. So we call DFS of 2, and that in turn we'll call DFS of 5. So at this point, when we get to 2, when we call DFS of 2, the first thing we do is mark 2, right? So when we go there, we'd mark 2, and then for every unmarked adjacent edge, or sorry, every unmarked adjacent vertex, we say, okay, the way to get there is through me. So in this case, it's 5, and then we'll go there. So we get to 5, and in this case, this is our that's not important. The phone's ringing, you can't tell. So at this point, we get to 5, and we say, okay, we'll mark 5, and then we'll say, is 2 marked? Yes, it's already marked, so we're not going to touch that, right? We don't want to change 2's edge 2. And then when we get to 4, we'll say, okay, oh, sorry, we look at all of our neighbors, and we say for each unmarked adjacent vertex, that's 4, 6, and 8, we're going to set the edge of that vertex. We're going to say the way to get to 4 is through 5. And we're going to continue doing all this again. I'm trying to convey the fact that yes, even though technically later we're going to try and set 6 and 8, even though we're going to later set 6 and 8, we're going to go to 4 first. Okay. So next up, after 4, we're going to call DFS of 3. That's going to be our next one. So same deal. We set 3 to true. And in this case, we don't set any of the edge 2's equal to 3. So if you've been watching this, maybe pause and think about that question. Why did none of these get set to 3? If you understand that question, you're following. Okay, at that point, we return from DFS of 3. I'm just noting it here. This is the first one that actually gets done. This is the first thing that we've explored fully. Okay, now we're back from 4. We've explored fully. We get back down to 5. And at that point, we have an unmarked child, or a neighbor. Oops. We have an unmarked child, 6. So we'll set edge 2 of 6 to 5. So notice I just changed that. And so we arrive at this position. Oh, and by the way, this demo is fully available online. So if you're tired of me talking and you'd rather not have my narrative, maybe explore on your own. It's linked in the slides. So here's 6. Then we go to 7. All right, at that point, we're done with 7. We return. Okay, how about 8? Well, in this case, we still have one more unmarked neighbor, which is 8. So we go to 8, mark it, and we set the edge 2 to 5, and then we do a bunch of returns. And so finally, we finished this entire graph processing process. And so what our Oracle effectively has done at this point has explored the entire graph. It's noted that every single vertex is reachable from 0. So this marked array, let's say it had vertex 9 over here that wasn't reachable, its marked value would still be false. But in this case, all the vertices were reachable, so they're true. So this right here means that our Oracle, we can ask it questions. Is 4 reachable? Yes. Does it have path 2? Indeed, of course it does. Look, the vertex is marked. Have an edge 2. We can use that to reconstruct a path. So for example, I ask the Oracle, how do I get to 4? Well, in that case, we say, okay, to get to 4, you use 5. Okay, how do you get to 5? You use 2. How do you get to 2? You use 1. How do you get to 1? You use 0. And in that way, our has-path-to algorithm, or sorry, our has-path-to method, sorry, one more time, our path-to method will be relatively easy to implement. Okay, so this is what the code might look like then. This Oracle, DepthFirstPaths, has 2 arrays, as I mentioned. Marked indicates whether or not it's connected. Edge 2 tells you how to get somewhere. The DepthFirstPaths constructor, I'm not showing the initialization of these data structures, but what it does is it calls a method that's private called DFS, which stands for depth first search. And that depth first search method behaves exactly as we just did in the demo. So what this recursive routine does, DFS, is it does the work and it stores the results in what I call an easy to query manner. Easy to query in the sense that given this marked array, I can instantly give the has-path-to method. How would we write it? Question to ponder. Okay, someone says, has-path-to 5, what do you do? Well, you simply return the 5th element of marked. How about path-to, or like give me a path to it? In that case, we'd have to do a little more work. And so, again, here's that little demo I just showed. It's on the slide, so look, here it is. Oops. And so this approach, this idea of searching a graph is very common and really cool, right? Like handing the graph to Oracle, having it sniff everything. I think it's a nice story. Okay? And so the properties of this approach, well, it's guaranteed to reach every reachable node. That will always happen. The runtime will actually be V plus E, the big O time. And I'll give the analysis next time, but the basic idea is that every edge is going to be used at most once. And the total number of vertices that you're going to consider is going to be, and the total number of vertices you have to consider is going to be equal to the number of edges. And you'll see what that means. But basically, it's just saying the number of times you need to consider a vertex will be no more than the number of edges incident on it. Now, the runtime may actually be faster for some problems. The reason I say big O of V plus E. So for example, let's say that instead of assembling the answer for the entire graph, we build a special purpose Oracle that only cares about connectedness from some source to some target. So instead of int s, it'd be int s comma int t. In that case, you could actually terminate the search early because you only care about that information. And in that case, maybe your runtime could be at best constant. So for example, if you ask, is s 0 connected to t equal to 0, then that would be very fast. Okay, so that's it for this lecture. So we're going to call it a day. I really encourage you to sit down with this demo and make sure it makes a lot of sense. And then make sure to check out the extra study guide problems linked on the website. I think that'll help you solidify your understanding of this lecture. Okay, so that's it for today, and I will see you next time.